Hey guys, so let's talk about energy conservation. So this is 5.2. That energy is a conserved quantity. So very similar to momentum. If you remember when we have an isolated system, the total momentum before is the same as afterwards. It's the same kind of thinking, except now we're going to talk about energies. So the objectives for this are to understand the conservation of energy principle, which is just what I just said, represent energy transformation. So now we're going to be using energy bar charts and then state and understand the work energy principle. So this is when we don't have an isolated system. We can just deal with the work. So let's look at this. In an isolated system, energy is neither created nor destroyed. And the key word here is isolated. So if we don't have any external forces, energy stays the same before and after. It's only transformed from one type to another. This is a huge idea in physics. So an isolated system will have all the energy inside of it is going to stay the same. Mathematically, all that this says is that the total energy before is going to be the same as afterwards. And for this level, when we talk about energy, we're going to be talking about mechanical energy. So that's going to be our only concern, is going to be mechanical energy. We're not going to worry about electrical or chemical or sound or anything like that. We'll get to that later in the year. But mechanical energy. So we have the gravitational potential energy. That's one of them, gravitational potential. And we'll use U with a little g. That's gravitational potential. That's misspelled, but you get the idea. Kinetic energy. And for kinetic energy, we'll use a KE. You can use K, but I like KE, kinetic energy. And then we have elastic potential. So remember, this comes from springs and rubber bands, things that are stretchy or can be compressed. And we'll use US for that. And then we have internal energy. Internal is really, primarily we'll be just talking about friction. So internal energy. So if a car comes skidding to a halt, some of this energy, the kinetic energy, will be transformed into internal energy. We'll use a U with little int. So what this says is that, my total energy, my UG initial plus my static initial plus my kinetic, I put these in a different order, sorry, plus the internal initial is going to be equal to all of that final. So UG final plus, go ahead and put kinetic energy, plus the elastic plus the internal. So we just add them up. They're going to be the same before and after. Now, just keep in mind that, if I have some gravitational potential energy, this doesn't mean that it stays the same afterwards. Okay, so I could have some gravitational potential energy, and then after some event, it gets transformed into like all kinetic energy. And that's what we're going to talk about. So this does not say that the amount of energy of one type stays the same. It says that the total stays the same. So one way that we can deal with that is using energy bar charts, and that will help us see the flow between the types of energy. So here we're gonna have a girl going down a water slide. So she's sitting at the top of a slide, and she comes down the slide. I don't know why it's blue. So she's up here, comes sliding down, and we want to analyze the type of energy that's being used or is in the system. The system here would be the girl and the earth. So one way we can do this is what's called an LOL diagram. This is one way of doing it. So you'll see, if you just want to do the bar charts, that's fine. But I do want you to identify the system and draw the system before and after. So LOL comes from, what we do is we're going to draw an axis like this, and then we'll use a big circle to define our system. And then we'll have, so this is the initial energy. And then we draw one afterwards. So we get an LOL. And this would be the final energy. So first let's do our system. Let me just label this so you know what we're doing. So before the girl slides, she's up at the top of the hill and she's not moving, okay? So this is her initial state. And the system is going to be the girl and the earth. We assume it's frictionless, so they're close to it. So we just have the girl and the earth. And then when she's done, when she's down at the bottom, she's moving with some velocity. So when she's standing still, since she's up here, you have the earth is going to be pulling on her. So what's stored is gravitational potential energy. And then as she slides down, all of that gravitational potential energy gets shifted over, gets transformed into kinetic energy, which is the energy of motion. So what we'll see is that her gravitational potential goes to kinetic energy. So we're going to have this transformation here. If you just want to do this type, that's fine as well. But this helps us see what's going to happen between here and here. So we have all of our gravitational potential being transformed into kinetic energy with no losses. So there's nothing external. There's no external forces. So this is an isolated system. Now our bar charts, this is how we'll do it. So I'll just keep it in the same order. We have our potential gravitational, we have kinetic, we have our elastic, and our internal. We go ahead and list them all so that we know that we're thinking about all of them and what happens, and that it goes the same over here. So to kinetic and internal. Right now we're just doing this qualitatively. There's no numbers. It's just trying to understand what's happening to the energy. So initially when she's up here at the top, lots of gravitational potential. So we'll just draw a bar chart. There's some gravitational potential. She's not moving, so there's no kinetic. So we'll just put an X there. That shows that, I thought about it, but there isn't any. Spring. So there's no elastic. There's no big spring that's going to shoot her off. So we don't have any of that. And internal, although there is some internal, when we talk about internal, we're going to be more concerned about the change in internal. So we would be working over here. So that's it. Okay, so her initial is all gravitational. And then she slides down and all of that gets transformed over to kinetic energy. So at the end, she has this kinetic energy. And just qualitatively, these are the same size. We're going to assume all of her gravitational potential was converted into kinetic. So we don't have any more gravitational. We never had it, and here you go. There's no friction, no loss to friction. So this is our LOL chart for this situation. And what we can see is that the sum here, all of this, is equal to the sum over here, all of this. And that's basically, that's kind of just where we want to be right now. It's just allowing us to see the movement between system. Now, what happens if what happens if it's not isolated? Well, we can still analyze it, and this is kind of like momentum when we had impulse, except now we're going to be talking about work. But it looks the same. So the work energy principle says that the net energy before plus any work done on or by the system. The difference between that, if it's done on, that's positive work. So we've added energy into the system, and if it's done by, then it's negative work. So we've taken some of the energy out, and that's equal to the total final energy. So if we break this out, our total energy is going to be our gravitational plus our kinetic initially, plus the elastic, plus the internal, plus any work done is equal to the final. And this is our work energy principle. Big idea. So if I take my total, I just add in the work, that will give me my final. Oh, I put an I, that should be enough. So let's see. Oops. Let's look at an example, and we'll do an energy bar chart for this. So stuntman jumps out of a window and lands in a large air cushion. So this guy's like, he's up on a building or something. There you go. And then he jumps off. And luckily there's a big air cushion that catches him. So we're going to take our system to be the guy and Earth. And I'm doing this intentionally. That puts the cushion outside of the system because we want to see what happens with external forces. So we start with our LOL. This one's going to be a little different though. And you'll see in just a second. And then we'll have our system. And then our final. So again, we have our initial state of everything, our system, and our final state. So let's start with the system. So the system is going to be this guy. And what we're interested in is this point right there. So what happens as he hits the cushion? So as he hits the cushion, he has some velocity. And then after he hits the cushion, his velocity is going to go to 0. So we're going to start with some kinetic energy, and then we're going to see what happens afterwards. So kinetic energy is going to be transformed, and what we're going to see is going to be transformed into, there's going to be some negative work done on it. Now the work comes because the cushion is external to the system. So the cushion is outside of my system. So the cushion, when he hits it, is going to be applying a force in this direction. Therefore, it does some negative work. So how do we draw this? So let's see. We have our potential. We have some kinetic. We have some elastic, our internal. And now we have work. Let me fix this. Let me spread it out just a little bit. So we go ahead and put work on here to show what's going on. And the work comes out of here. Over here, we have kinetic, elastic, and internal. No work on the right-hand side. Work is only before. Kind of it comes between. Okay, so the guy's falling. Right when he hits it, he has a whole bunch of kinetic energy. He has kinetic energy. However, the cushion is going to do some negative work on him. So we're going to have some negative work. And what I can see is that, so there was no internal, no spring, no gravitational. I can see all of his kinetic work. If I were to add these up, if they had values, you could see that these would cancel out, which resulted in no energy in the object, in our guy. So adding these up would equal to 0. This is basically, it's basically all there is. You're going to need a lot of practice with this. Hopefully the bar charts help you see the flow of energy, both within a system being transformed and also in and out of a system. So the key here is to identify, is it isolated or not? If it's not isolated, we might have some work that's done on or by the system. And that's it.